Good morning, guys. Welcome back. So we're moving through our trigonometry unit. So again, guys, the trigonometry unit is divided into 3 chapters. First chapter is called the unit circle, and so we do trig ratios, unit circle. We kind of started doing some basic trig equations. Chapter 5 was all about understanding trigonometric functions. So there's a graph of y equals sine x and a graph of y equals cos x. The last unit, chapter 6, is called trigonometric identities. So what this unit is all about is we're trying to prove that certain trig expressions are actually equal to other trig expressions, okay? And when I say prove, guys, we're kind of using, I'm going to say, a more formal mathematical technique for proofs, which we call two-column proofs, okay? So we need to kind of be able to find a way to show that one side of an equation is actually is indeed equal to another side of the equation over there. Now, reason we do this, down the road, like I can say specifically in calculus, there's going to be certain cases where if you can take one more complex trig equation, it makes it much beneficial to be able to replace that with a simpler trig equation as well. And so we study the ways in which we can show that different trig expressions, different trig equations are in fact equivalent to each other, and how we do that. Okay, so first topic is called trig identities, and so we'll get into that. So for example 1 here, with a graph y equals sine x and y equals tan x times cos x. Great. In a second, guys, we'll have 4 decimals here because it's going to. So when I'm going to graph, I'm just going to adjust my window settings here, and I'm going to say from negative 4 pi to 4 pi, let's get pi over 2, and I'm just going to go from, say, negative 2 to positive 2 here. Make sure I'm going to say that we're in radians for this question here. I'm going to go ahead and graph y equals sine x, okay? So like we saw in the last unit, we have this sinusoidal function over here. It's producing this kind of wavy graph over here. The period of this graph is 2 pi, the amplitude is 1. The sine graph is going up through the origin for just y equals sine x. Now, what it's saying is, with the graph y equals tan x times cos x. Brackets, I'm going to be careful here. So what I'm trying to get at, for example, if you look at the green graph, which is y equals sine x, and the purple graph, y equals tan x times cos x, we're actually seeing 2 directly overlapping graphs. Okay, so what the graph is kind of suggesting here is that this expression of sine x is going to be equivalent to the expression of tan x times cos x. Okay, so now why is that? And they actually equal, and what we're going to find out in a second is that, well, I'm going to say that they're almost always equal. Okay, and when I say almost always, because there's a few exceptions we have to account for over here. So what we saw in, just filling up my notes here. We have sine x, and we saw the graph that was looking like this. So this was y equals sine x, and then y equals tan x is the same thing, just draw an overlapping graph like this, and this is also going to be y equals tan x cos x. Okay, all right. So for part B, it says verify that sine x equals tan x times cos x when pi x equals pi over 6. Bear with me for a second, here, guys. I'm just going to pull up another note over here. If we look at our mathematics directing words page, give me a second, guys. Sorry, I was going to log back in. So this is a sheet that in my class we've referred to a few times, but verify is one of the mathematics directing words we have. So it says establish by substitution for a particular case or by geometric comparison the truth of a statement. Okay. All right. So establish by substitution. So in other words, what this means is we have to substitute values for a particular case. Now, what it says over here, this is for a particular case. This is not necessarily for all cases over here. Okay. So we'll come back to our case over here. So what this is, what means verify, is we want to so what we're going to do is we're going to take this pi over 6 and we're going to slip it into the x's that we see in this equation here. Okay, so this work over here. So this is what we're doing here. Now, what I'm going to do over here, I'm just going to put a line through the middle here. Now, when we call a two-column proof, we're going to show that something on the left side equals something and something on the right side equals something. And then once we've shown that they are the same, we've kind of done what we need to show here. So I'm going to put in a pi over 6. We have sine pi over 6. And then we have tan pi over 6, cos pi over 6. So quick little unit circle off to the side over here. But at pi over 6, we have this point, which is root 3 over 2, comma, 1/2. Okay, so guys, you're going to be using your unit circle a lot in this unit over here. So if you're not an expert at writing out your unit circle, guys, you need to be, because we will be referring to this guy all the time. So what's sine pi over 6? Sine pi over 6 is the y coordinate at pi over 6. So this value is equal to 1/2. Okay. Now tan pi over 6 is sine over cos. So just off the side here, tan pi over 6 is 1/2 over root 3 over 2, which is 1/2 times 2 over root 3. So these 2's cancel out, and we're left with 1 over root 3 is tan pi over 6. Now, cos pi over 6 is root 3 over 2. So we multiply times root 3 over 2. What happens here is this root 3 can cancel out with this root 3 here, because we're multiplying, and we're left with 1/2. Okay, so if I put this equal, so now I can kind of put this equal sign. So really what we're doing here is like we're verifying this equal sign is indeed in fact true for x equals pi over 6. Okay, so again, what verify meant, it says establish that a case is true by substitution. Okay, so we kind of substituted in our value over here, and so we said yes. So when x equals pi over 6, sine pi over 6 does indeed equal tan pi over 6 times cos pi over 6. All right, so for example C here, prove that is equal to all values of x. Okay, now, sorry guys, pull up our formula sheet as well. Another thing that we're going to be using regularly in this unit is your formula sheets. And I'm just going to go ahead and copy a couple of these. All right, so all I'm just doing here, I'm copying our tan equals sine over cos, or cotangent equals cos over sine. We're just going to be using this one in this example over here. So using this was from our formula sheet. When we prove these guys, we're going to do it again with what we call a two-column proof. So I'm going to put a line down the middle like this. Okay. Now, really, there's not much we can do on the left-hand side. This side is just going to be sine x. So sine x is going to stay over here. Now, but what can we do on the right-hand side? Well, here for tan x, we have an identity. And so we have spoken about this before, but we know that tan is equal to y over x in terms of this same thing as sine over cos. Right? So sine over cos, what we're going to do is we're going to make this substitution here. And we're going to take tan and replace it with sine theta over cos, sine x over cos x. So this is going to be sine x over cos x times cos x. And what we see here is these coses cancel out. Okay, so now on the right hand side we have sine x. So if on the left hand side I have a sine x, and the right hand side we have a sine x over here. Okay, so we've shown that the left side equals the right side. Okay, now in the Alberta education, this is often like a written response type question on a diploma exam. They wanted to see this sort of concluding statement at the end. If you're saying left side equals right side, you've shown that, well, so you've shown that the left side equals the right side, therefore these are actually going to be equivalent expressions. Okay, so we're going to say that the left side equals the right side, and I'm going to explain this more in a second, guys, but this symbol is a math symbol that we use to denote the completion of a proof. Now, we could put instead, pardon me here, guys. This QED is a Latin phrase, which means which was to be shown. Okay, and so this is what we use to kind of denote the end of a proof. Now, this tombstone means the exact same thing, right? So it's when you finished a proof, we're going to either put this square, which means we've completed the proof, or we can say that just QED, which means it both mean the same thing, which was to be shown. Okay. Now over here, what non-permissible values do we have to consider? Okay, so like we did in math 20, we spoke about non-permissible values quite a bit, and like if we're looking at the cos x, which is in the bottom, so we know that first of all, we know that tan x has vertical asymptote, okay, because the bottom of a fraction is not allowed to equal 0. So when cos x equals 0, that means x equals pi over 2 plus pi n, where n is an integer. Now I'm getting this just off my unit circle again. So where does cos equal 0? Here at pi over 2 and 3 pi over 2. So this is like 0, 1, and 0, negative 1. Okay, so these two spots over here, so it's going to be pi over 2 plus pi n. So this one, and I guess what I should say is cos x cannot equal 0. Therefore, x cannot equal pi over 2 plus pi n. Okay, so this is true for all values of x except for these guys over here, because when we have these values over here, tan is actually undefined. Well, sine is allowed to equal pi over 2 plus pi n, but tan is not. So therefore, this identity is not true for these values over here. All right. So I'm going to say this is going to be a classic type of multiple choice question that you'll see. It's going to give you an expression like this, and it's going to give you like A, B, C, D. Which option is equivalent to this expression over here? Okay, so we have cotangent, secant, cosecant, and cotangent. Well, what we can, I guess, the general thing that we're going to do for a lot of these questions is we want to be able to put everything in terms of sine and cos. So I'm just going to look back to my formula sheet here. And I'm going to copy all of these guys on my page. So we're going to use all of these in this question here. All right, so cotangent x is the same thing as, well, same thing as 1 over tan, but it's also the same thing as cos over sine, okay? So guys, general strategy is you want to make everything in terms of cos over sine that you can. So doing this, I'm just going to replace cotangent x with cos over sine. Secant x is the same thing as 1 over cos, okay? And then we have cosecant x, I'm just going to put times here. Cosecant is 1 over sine, so I'm going to make this substitution here. And cotangent, again, is cos over sine here. Okay, a few ways I could do this over here, but what I'm going to do is I'm going to simplify this fraction, simplify this fraction, and then multiply those fractions together. So for the first one, I'm just going to do this off to the side here. We have cos over sine divided by 1 over cos. So we get cos over sine. Now, if I'm dividing two fractions, I want to multiply by the reciprocal. I'm going to make that cos over 1. So this is going to be on the left-hand side over here. We're going to have cos squared over sine. And that's what cos over sine divided by 1 over cos is going to equal this. Now, 1 over sine divided by cos over sine. I'm multiplying by the reciprocal here. So the reciprocal of cos over sine is sine over cos. Those guys cancel here. So we have times 1 over cos. And then this cosine cancels out with one of the cosines on the top. And so this equals cos over sine. And we know that cos over sine is the same thing as cotangent. So this is equal to cotangent x. Okay. Now the idea here is like this expression, quite, I'm going to say more complex than this than just cotangent x over here. So we've been able to simplify this fairly nasty expression down to something much simpler over here. Okay, so in order for it, we've simplified this guy. Now, what else do we need to do? We need to state non-permissible values. Okay, so all we're going to do is look at our denominators. We have a denominator here, 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 here. Also, this is a denominator, and this is a denominator here. Okay, so what do we have? We have sine x cannot equal 0. We have cos x cannot equal 0. And if I look at this one over here, cos over sine, well, this is 0 when cosine equals 0, but I've already accounted for this guy over here. This guy is never going to equal 0 because I'm going 1 divided by something, so it can't be 0 over there. So I just have to account for when does sine x equals 0, when does cosine equals 0. And that happens on the axes here, 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 and here. So we're going to say this. So this is like 0, pi over 2, pi, 3, pi over 2, and so forth. So our non-permissible values are going to be x cannot equal pi over 2, n, where n is an integer. That's how we state all of our non-permissible values. All right. So prove the identity sine squared plus cos squared equals 1. Look, this guy is on our formula. So in my class, guys, I generally have a rule that I say that anything that's on your formula sheets is free. Okay. What I mean by free is you don't have to prove it. Now, we are going to prove why this one's true. Okay. But like once I've proven this one over here to you in class, guys, anything, all of these guys that you can use here, you're allowed to use. You don't need to justify why you're using it. Say, well, this is an identity. It's been shown to you in class, so you're allowed to use it now. Okay. So like I say, you're allowed to use it for free. Okay. But sine squared plus cos squared equals 1 is what we call, I say all three of these are called our Pythagorean identities. And I'll show you why it's called a Pythagorean identity in a second here. Let's find a better one than that. I'm going to include this one. All right, so here are 3 Pythagorean identities over here. Okay. Now, the way we're going to prove this one is we're going to use a little bit of coordinate geometry here. The way we defined sine and cos earlier on, so back in our chapter 4, which is our trig unit circle chapter, in the unit called trig ratios, we know that if you have any point on the coordinate plane, and say I can call this guy over here xy, then if I draw an angle in standard position, and this is angle theta in standard position here, guys, it does not have to be in quadrant 1, it could be in any of the quadrants over here as well, then we have x, y, and r. Okay, so defining this, so in terms of like SOHCAHTOA, which is our basic primary trig ratios, we have cosine theta equals x over r, and we have sine theta equals y over r. Okay. Now the other thing we have with these three, with x, y, and r here, is we have just Pythagorean theorem, which is so there's like a squared, b squared, c squared, but it's x squared plus y squared equals r squared. We've talked about this. It's kind of the equation of a circle as well. Okay. So what we have here is we have sine squared plus cos squared. So I'm just going to do a two-column proof for this guy here. So again, guys, a two-column proof is really what we're doing is we're verifying this equal sign is in fact equal. So what I'm going to do is I'm going to put a line through the middle, and we need to show that the left-hand side does in fact equal the right-hand side. Now we know that sine theta is y over r. So sine squared theta is going to be the same thing as y over r squared. And cos squared theta is x over r squared. So this is going to be the same thing as y squared over r squared plus x squared over r squared is y squared plus x squared over r squared. Okay, so all I did here, we have common denominators of r squared, so we can add the numerators like we have here. Well, let's see here, what's x squared plus y squared equal? Over here, we have x squared plus y squared, and we know that this, in fact, equals r squared. So we're going to make this substitution here, and we now have r squared over r squared, which equals 1. Well, this is what the right-hand side of the equation equals. So we have a 1. So we have, I'm going to box this guy up now, because we have proven, and I'm going to go like the left side equals the right side. So therefore, we have proven what we needed to prove. Okay, so this is what we call our Pythagorean identity. And guys, we use this one a lot. Sine squared plus cos squared equals 1. Now, we'll get to these ones in a second. These are going to be kind of variations of the Pythagorean identity over here, but we'll get to how we do these ones in a second as well. Here we go. 1 plus tan squared equals secant squared. So here's a few identities that we're going to need to use for this one. Guys, these are just right off your formula sheet as well. We're going to be using these three identities for this question. So for the first one, 1 plus tan squared equals secant squared. I draw a line down the middle, two-column proof. Now what I'm going to do on the right-hand side is, I know that secant squared is the same thing as 1 over cos squared. Okay. Now over here, I know that tan squared is equal to sine over cos. So that means tan squared is the same thing as sine squared x over cos squared x. So what I have here is that the number 1 plus a fraction. I'm going to make 1 over 1. And in order to get a common denominator here, I'm going to multiply the top and the bottom of this fraction by cosine squared. So that leaves me with cosine squared over cosine squared, equivalent to 1. And now I have a common denominator of cosine squared. And we're left with cos squared plus sine squared over cos squared. Okay, well, what did we prove in the last example? Sine squared plus cos squared equals 1. So I'm going to make this substitution in here. Okay, and now it's going to be the same thing as 1 over, so I'm replacing cos squared plus sine squared with 1 over cos squared. And that is what the same thing I have on the right-hand side. Okay, so therefore the left side equals the right side, and in this case, put QED. Whether you put QED or a box at the end, it doesn't matter. But this is kind of the concluding statement, which means we've shown that the left side equals the right side, which is what we're trying to do. Okay, so we're trying to show that this is indeed equivalent to this over here. Okay, so guys, what I said before, these identities that we have, anything on your formula sheet you can use for free. Okay, so again, here, for example, 3 and 4, we proved why they're the same. Okay, but really, guys, anytime you see something similar to one of these on a formula sheet, when I say similar, it means you may have to do a slight manipulation. Like this identity over here is equivalent to like tan squared equals secant squared minus 1. So all I did was, I subtracted 1 from both sides of the equation here. So this is equivalent to this guy over here. Okay. So these equations, and if you manipulate these equations like that, you're allowed to use those in the proofs we have going forward. All right, simplify the following trig expressions. Okay, cotangent x, sine x. Okay, so again, step 1 is we want to put everything in terms of sine and cos. Cotangent is equal to cos over sine. Okay, so I'm just going to make that substitution here. Cotangent is cos over sine times sine x. These guys cancel out. So this guy equals cos x. Okay, now we have to have one more condition here. We have non-permissible values because we have sine x in the denominator. So that means that sine x cannot equal 0. And off our unit circle, where does sine equal 0? Well, it equals 0 here and here. Right? So this is 0, pi, 2 pi, 3 pi, and so forth like this. So therefore, x cannot equal, we're just going to call this guy pi n, where n is an integer. Sound good? Okay, so this is cos x, but we have some restrictions for the values of x because for these values, that means this is not defined, even though this is defined. For these values, this guy is not. So we can't make this substitution for all values. We have to exclude these values right here. Cotangent over cosecant over secant plus 1. Okay, so this one's going to be looking quite a bit more difficult over here. Let's see what we can do. We know that cotangent x equals cos over sine. And these are all off your formula sheet again, guys. We know that cosecant x is 1 over sine. And we know that secant x is 1 over cos. Okay, so we're going to use these three identities here. All right, cotangent. We have cos over sine plus 1 over sine. Guys, I think one of the hardest things about this unit, like the trig part, like after a while, guys, you can recognize these substitutions right away. The hard part is actually dealing with the fractions properly. Okay, so fractions is hard, and then later on, guys, we have to do some factoring. Okay, so factoring and fractions are two of the math F words that we have in this course over here, right? So kind of getting used to these guys is a little bit tricky here. In the numerator, we already have a common denominator. Okay, so the sign here and a sign here, so we can add the two numerators, and that's just going to be cos x plus 1 over sine x. In my denominator, I need to get a common denominator. I'm going to multiply the top and the bottom here by cos x. So that's going to give me 1 plus cos x over sine x. Okay. Now I'm dividing two fractions. I'm dividing this fraction by this fraction. So I'm going to multiply by the reciprocal. That means the top fraction stays the way it is. So it's going to be cos x plus 1 over sine x times sine x. Guys, I made a mistake here. This is 1 plus cos x over cos x, not sine x. hopefully what you're seeing is that we have a cos x plus 1 in here, and then 1 plus cos x. Well, these guys are actually the same. So these guys can cancel out, and that means we're left with cos x over sine x, which is the same thing as cotangent x. Okay, now we have a bunch of denominators in this whole proof over here. So we need to go and figure out what non-permissible values we have. Well, we know that sine x cannot equal 0. Okay, and that's based on this one and this one. We have cos x cannot equal 0. We also have, this is the denominator, and like if the numerator is 0, that means this is 0, which means the whole denominator is 0. So it means we have cos x cannot equal negative 1. Okay. Now, I think some of these are, a couple of these are going to be repeats here. Where does sine x equal 0? Here and here. Where does cosine equal to 0? Here and here. Where does cosine equal negative 1? Well, that's this guy over here again. Okay, so we don't need to count it twice. But all of the axes points are going to be non-permissible values. So therefore, we have x cannot equal pi over 2n, where n is an integer. All right, hope that makes sense. Okay, prove the following trig identities. We have sine squared minus 1 over cos equals negative cos. So here's where we're going to go for this guy. We're going to refer back to our Pythagorean identity, which is cos squared theta. Sorry guys, I'm just going to do it. I think on your formula sheet it says sine squared first. It doesn't matter, but it's the same thing. What we need to start getting good at recognizing is sine squared minus 1 is not anywhere directly on our formula sheet, but we can get there by manipulating this formula over here. If I want sine squared minus 1, how do I get there? Well, if I just go and subtract 1 from both sides, and then subtract cos squared from both sides, we get sine squared minus 1 equals negative cosine squared. Okay, so manipulating the Pythagorean identity, we're going to now make this substitution here. So sine squared minus 1 is being replaced by negative cosine squared. So again, two-column proof. Okay, we're making this substitution here. We have negative cosine squared over cosine theta. And now cos squared over cos, get some cancellation. And we're left with just negative cosine theta equals negative cosine theta. The left side equals the right side, okay, which was to be shown, QED. So here's our completing statement we've shown, which we've needed to show here, okay. We do have non-permissible values to account for. We have cosine in the denominator here, therefore cosine cannot equal 0. And where does that happen? It happens here, which is pi over 2 and 3 pi over 2. So therefore, theta cannot equal pi over 2 plus pi n. All right. So guys, this unit over here, it takes a lot of practice. Okay, and I mean, just you need to be really, I'm gonna say, crisp with your factoring skills, crisp with your fraction skills in general as well. Okay, so cosecant squared plus secant squared equals cosecant squared times secant squared. Okay, so how are we going to get this guy over here? Well, we have cosecant squared, which is the same thing as 1 over sine squared, and plus secant squared is 1 over cos squared. Well, on the right-hand side, this is 1 over sine squared times 1 over cos squared, which is like 1 over sine squared times cos squared. Okay, So we've kind of simplified our right-hand side down to this expression over here. On the left-hand side, we're adding two fractions. We do not have a common denominator. My first term needs to have a co-squared in the bottom. So I'm going to multiply times co-squared over co-squared. On the other term, I'm going to multiply times sine squared over sine squared. Now what this gives us here is we have a common denominator of sine squared co-squared. And in our numerator, we have sine squared plus co-squared. Now our Pythagorean identity, we're replacing co-squared plus sine squared with 1. The left side equals the right side, which was to be shown. Okay. All right, last thing, non-permissible values. Guys, I know these are often the same non-permissible values every time, but we have sines and cosines in our denominator. So therefore, sine squared cannot equal 0. That means sine cannot equal 0, and cosine squared cannot equal 0. That means cosine cannot equal 0. It happens at the axis points again over here. So our restriction over here is theta cannot equal pi over 2n, where n is an integer. All right, guys, good luck with your practice on this section over here, guys. And if you have any questions, guys, please come and let me know or send me a message, and I'd be happy to help you out with those ones, guys. And I will see you in the next video.